So we have seen what is the distance of closest approach, that is the distance where the alpha particle will stop near the nucleus due to the repulsive force. So now we will see how to find out the distance of closest approach. How to find out the value of D. So this is the alpha particle and this is the nucleus. When the alpha particle approaches the nucleus, it stops at a certain distance. We call it D. Okay. At this point, velocity is 0 because alpha particle stops. So we have told that the mass of the alpha particle is m, velocity is v, and suppose this nucleus has a charge of Ze plus Ze, where we know the value of E is 1.6, since it is positive, so plus 1.6 into 10 to the power minus 19 coulomb, and Z is the number of protons in this nucleus. Number of protons, okay. So if total number of protons is Z, then the total charge will be Ze, okay, and E is the charge of one proton. If V is 0, we know that when a particle is moving, it has kinetic energy. Kinetic energy, Ke. Ke is written as half of mv square. Now at this point, if V is 0, then kinetic energy will also become 0. But by the law of conservation of energy, we know that energy cannot be created nor can it be destroyed. Energy can be converted from one form to another. Okay. So here, if kinetic energy is 0, then what is the force that is acting between the alpha particle and the nucleus? That is the repulsive force, right? Repulsive force. What is this repulsive force? Since they are like charges, they repel. This is repulsive force is actually electrostatic force. So the kinetic energy is converted to electrostatic potential energy. Which is written as K Q1 Q2 by D, where D is the distance between two charges. Here this is the distance of closest approach. Okay. So E initial equal to E final, since energy is conserved. What was E initial? Initially when the particle was moving, it was having a velocity v and kinetic energy half mv square. So, kinetic energy has been converted to electrostatic potential energy. This is the E initial and this is the E final. So, E initial is equal to E final. E initial was half mv square and E final is k q1 q2 by d. We have to find this d. So, what is k? K is a constant. K has a value of 9 into 10 to the power 9 Newton meter square per column square, that is column to the power minus 2. The mass is in kg and velocity is in meter per second, and we know the value of q1 and q2. If q1 is the alpha particle, what is the alpha particle? Alpha particle is helium, right? Helium with a charge of plus 2. So, q1 is 2 into this charge, right? This charge is written as small e. So, q1 equal to 2e. And what is q2? If q2 is this nucleus, what charge the nucleus was having? Ze, where Z is the number of protons in the nucleus. So, q1 equal to 2e, q2 equal to Ze. Okay. So, this is the final statement, half mv square equal to k into 2e into Ze by d. So, d equal to 4k Ze square by mv square. This is the statement for the distance of closest approach. Now, we will finally go to Rutherford's nuclear model. What were the statements? Okay. So, the first statement was the positive charge and most mass of the atom is concentrated in a small region called nucleus. The second statement was nucleus is surrounded by electrons that move around in very high speed in circular paths called orbits. Let's discuss the third point. The third point was electrons and nucleus are held together by force of attraction, by electrostatic force of attraction. Why? Because the electrons are negative, nucleus contains positive charge. So, nucleus are positive. Nucleus contains the protons and neutrons. Okay. So, nucleus is a very small region in the atom. Nucleus contains proton and neutron, and electrons move in orbits, circular orbits. So, Rutherford's atomic model was kind of similar to the solar system. We know that in the solar system we have the sun at the center and the planets move in different orbits, right? These are the planets. In Rutherford's atomic model also, the atom had a positively charged nucleus which contained protons and neutrons, and the electrons moved in circular orbits. So, this was the nuclear model of Rutherford. With this, there are two terms. What are the two terms? Atomic number and mass number. You must have heard about these two terms, the atomic number and mass number. What is the atomic number? Atomic number is the number of protons in an atom. Since the atom is neutral, so the number of protons should be equal to the number of electrons. So, this is equal to the number of electrons. If number of protons is P and number of electrons is E, then this is the atomic number. This is represented by Z. Remember, we had said that Ze is the charge of the nucleus. This Z is actually the atomic number. And what is the mass number? See, the nucleus contains protons and neutrons. So, the mass number which is represented by A is the sum of number of proton and number of neutrons. So, P plus N is the mass number. Okay. If suppose an element, let's consider it as M, then it is written in this configuration. Mass number A is written at the above and atomic number Z is written at below. So, all this while when we were representing alpha particles, that is heliums, like this, we were actually representing the mass number and atomic number. Mass number of helium is 4 and atomic number of helium is 2. So, if we consider some examples like hydrogen, hydrogen has mass number equal to 1 and atomic number also equal to 1. That's why H plus was proton. Why? Because mass number is proton plus neutron equal to 1 and atomic number is proton equal to 1. Therefore, number of neutron equal to mass minus atomic number. So, 1 minus 1 equal to 0. Therefore, hydrogen has no neutron. That's why when we take one electron out from hydrogen atom, it becomes a proton only. Okay. So, just another example, carbon has mass number of 12 and atomic number of 6. So, what is the number of proton? Number of proton is the atomic number, that is 6. What is the number of electron? This is equal to proton, that is also 6. And what is neutron? Neutron is 12 minus 6, which is equal to 6. We will do some more examples in the next lectures. Thank you.